Way up high in our stratosphere, there's this incredible shield protecting, well, all of us. It's the ozone layer. But here's the thing. It isn't some static, unchanging wall. It's actually in a constant state of flux, this delicate chemical dance of creation and destruction. Today, we're going to dive right into the chemistry of that balance and see how easily it can be thrown completely out of whack. So that's the big question, right? What is it that actually maintains this protective layer? How does it manage to keep itself stable day in and day out? And the answer is it's this beautiful, self-regulating cycle. It's a natural process where ozone is constantly being made and then unmade, and the whole thing is powered by the sun itself. Now, this isn't some kind of flaw in the system, it's the design, and it's worked perfectly for ages. Okay, so let's get into the specifics. This natural cycle actually has a name, and it's the absolute foundation for understanding everything else we're going to talk about. It's called the Chapman mechanism. Think of the Chapman mechanism as the atmosphere's default setting. It's basically the set of chemical reactions that, under normal conditions, keeps the amount of ozone up there pretty constant. It's the natural state of equilibrium. Let's break it down. It really comes down to two main parts. First up, creation. You've got this super high-energy UVC light from the sun, and it zaps an oxygen molecule, that's O2, and splits it into two separate oxygen atoms. Then, one of those free-floating atoms bumps into another O2 molecule, and bam, you get O3. That's ozone. But, like I said, it's a two-way street. That brings us to step 2, destruction. Weaker UVB light can come along and break that new ozone molecule apart. Or an ozone molecule might just collide with one of those free oxygen atoms, and they'll naturally recombine to form two regular O2 molecules. And here you can see that whole process in one continuous loop. On one side, you have creation, all powered by the sun, and on the other, you have this natural destruction. It's this constant give and take that maintains our protective ozone layer. It's such an elegant, self-sustaining system. But this perfect balance is also surprisingly fragile. So what happens when something new gets thrown into the mix? And this is where our story takes a pretty dramatic turn, because that natural balance can be violently, catastrophically disrupted by something called catalytic destruction. So what on earth is a catalyst? Well, in chemistry, it's a substance, we're just going to call it X for now, that dramatically speeds up a reaction, but it doesn't get used up in the process. It's like this little chemical agent of chaos that can cause damage over and over and over again. In our story, these catalysts are a special type of molecule called a free radical. Just think of them as hyperreactive and unstable, desperately looking to steal an atom from another molecule. And ozone is their absolute favorite target. Let's just pause for a second to really let the difference here sink in. The natural process, it's slow, it's simple, it's basically a one-for-one trade. But a catalytic reaction, whoa, that is a whole different ballgame. A single catalyst molecule, just one of these X's, can kick off a chain reaction that destroys thousands, sometimes even tens of thousands of ozone molecules. It's destruction on a completely different level. It's hyper-efficient. So how does this incredibly efficient destruction actually work? Well, there are two main ways it happens. The first is what we call mechanism I, and this is the one that takes place way up in the upper stratosphere, where there are plenty of those free oxygen atoms we saw earlier floating around. Okay, check out these steps. First, our catalyst X slams into an ozone molecule, O3, and just rips off one of its oxygen atoms. This destroys the ozone, of course, and you're left with a regular O2 molecule and this new temporary molecule, XO. But here's the kicker, the really crucial part. In step 2, that XO molecule finds a lonely free oxygen atom and basically hands off the atom it just stole. And what's the end result? The original catalyst, X, is spit back out, completely unharmed, and totally free to go hunt down another ozone molecule. The cycle begins again. But wait, what happens a little lower down in the stratosphere, where those free oxygen atoms are a lot harder to come by? Well, the catalysts have a completely different and arguably even sneakier strategy for this environment. It's called Mechanism 2. This is where things get really clever. See, Mechanism 2 doesn't need any free oxygen atoms at all. Instead, it uses a kind of tag team approach with two different catalysts. We'll call them X and X prime. So, as you see in the first two steps, each catalyst goes off and steals an oxygen atom from two separate ozone molecules. Then, in the final, brilliant step, the two temporary molecules they formed, XO and X''O, they find each other and react. This collision frees up both of the original catalysts, X and X prime, sending them right back out to hunt for more ozone. The net result, 2 ozone molecules get destroyed every single time this cycle runs. And this slide really puts it all together perfectly. On the left, you've got mechanism I, which needs that free oxygen atom to reset itself. And on the right, you've got mechanism 2, the tag team approach that works without it. 2 different chemical pathways, but they both achieve the exact same thing, incredibly efficient ozone destruction. All right, so we've looked at the natural balance, and we've seen the chemical machinery that can just tear it apart. But now for the most important question of all, why does any of this matter? This quote from the source material just hits the nail on the head. The entire problem, the whole reason we even talk about ozone depletion, comes down to one simple, unavoidable fact. We, as in humanity, have been pumping gases into the atmosphere that turn into these X catalysts. We have been artificially tipping the scales, supercharging the destruction side of the equation. So who are these chemical bad guys? Well, the main culprits are free radicals that contain chlorine and bromine atoms. These are the real-world X catalysts we've been talking about, and their intense reactivity all comes down to having an unpaired electron. This makes them incredibly aggressive, always looking to rip an atom off a stable molecule like ozone. They are the engine of this hyper-efficient destruction machine. So when you step back and think about it, a single chlorine atom can wipe out tens of thousands of ozone molecules, totally overwhelming the natural creation process. It just goes to show you how fragile our planet's protective shield really is. The chemistry is this finely tuned balance, and for a long time, we were the ones introducing the catalyst for its destruction. And that forces us to ask a really critical question. What happens when we decide to become the catalyst for change?